Hi, a little while ago I did a review of this Agilent 344618 multimeter, and as part of the review I was playing around with a 9-volt battery like this, and I made note of the fact that the reading was dropping like that, and that was due to the 10 meg input impedance of the multimeter. And somebody in the comments, sorry I forgot who it is, mentioned that oh no, that was me holding the battery. That was my the heat from my hand holding the battery that was causing the voltage to drop. Well, no, that's not the case. It is actually the input impedance of the multimeter. So I thought we'd actually take a quick look at this and just have a little play around with some basic multimeter loading on various batteries like this. Now, because this multimeter is 6.5 digits, we've got, for a 9-volt battery here, we've got 10 microvolts resolution here, which is excellent, and we can actually get greater resolution than that, as I showed in the review, by using the data logging and trend plot function as well. And you can see it dropping now. Now, this multimeter, like many good high-end bench multimeters and also handheld ones at all, it's got two different types of input impedance. It's got 10 meg standard, as your regular digital multimeter will have 10 meg input impedance, and that's what we're loading down on this 9-volt alkaline battery at the moment. But it's also got a high impedance mode here, or high Z. It says auto, but what it's jumping to is actually high Z. You can see that on the display there. You'll notice that the voltage is now jumping back up because there's much less load on there. In the case of this particular multimeter, the datasheet just says it's greater than 10 gigohms. So there's a huge difference there, and but this should be enough to let us just play around with a couple of batteries here and note some interesting things. So let's take a look at it. Now, as you may know, a brand new alkaline cell, or alkaline manganese dioxide, is the typical chemistry used in these most alkaline batteries these days. Then the open circuit cell voltage can effectively vary from anywhere from the nominal 1.5 volts per cell, or 9 volts in the case of this 9-volt battery, which has 6 4A cells effectively inside it. If you open up one of these, you'll find 6 physical 4A size alkaline cells in there. But that can vary from 1.5 volts per cell up to about 1.65 volts per cell, or for a 9-volt battery up to 9.9 volts open terminal voltage. And this large variation is due to the electrochemistry inside the cell and the purity of the chemicals in there and the materials and oxide layers and layers that form on the plates, and all sorts of stuff like that. So it does vary a fair bit, and that will come into play when we try and measure the internal resistance of a battery like this, just using the load on our multimeter here. Now, if you have a look at the datasheet for a typical Duracell alkaline manganese dioxide battery, i.e. your typical alkaline battery, they're pretty much all the same. The brands, really, there is not going to be a huge amount of difference. All the typical values are all going to be the same. Now, the Duracell one happens to tell you the internal impedance of this thing. There it is, 1700 milliohms, or 1.7 ohms. Now, that value of the internal impedance is actually fairly consistent across the life of the battery. It really doesn't change much at all, and that's the basic electrical contact resistance inside the cell itself. Now, this is really a key point because it's specified at 1 kilohertz here, and the reason it's specified at 1 kilohertz is because it doesn't include what's called the ionic resistance, or the electrochemistry effects, as I often call it, inside the cell. So that's why, if you really want to measure the internal impedance of the battery, the internal ES, some people call it the ESR, then you have to do it very quickly at a rate around about 1 kilohertz or thereabouts. It can be a bit slower than that, but it can't be in the order of seconds. So it's not like you can hook up your battery and then a couple of seconds later take a measurement and then, do your Ohm's law calculations and see if you can calculate that 1.7 ohms, because you won't get it. Because over the longer term period of hundreds of milliseconds to seconds to minutes to hours, it's the ionic resistance or the electrochemistry effects inside the battery that dominate. So that internal impedance is only valid at those very short time periods there. Now that warrants a separate video in its own right, how to actually measure and confirm that internal impedance. We won't be able to do that here today because, as I said, you've got to do it very quickly. You usually have to set a stable. It's usually done with a pulse load, where you set a stabilizing pulse and then you drop the load right down, and then you measure it straight away, and then you take it back up really quickly at near that 1 kilohertz rate. But if we have a look at the typical discharge characteristics of this cell, it's not that 1.7 ohms, that value of the ESR that's increasing under load, that's causing the discharge of this cell. It's mostly the ionic resistance at play here over these long time periods. And you'll notice that it actually starts very high and then ramps down very quickly. It's not very noticeable on this one, but if we jump over to an Energizer datasheet, once again for the same 9-volt battery, you can actually see down here where this one's, you know, not a particularly high load, and it is pulsed. And in this case, it's 10K/620 ohms, 1 second pulse per hour. So, you know, a fairly light pulse load. And you can really see the rapid drop in the value here. And that's the electrochemistry or ionic resistance coming into play. And not only does it come into play over days, like we've got here, you'll also and at fairly high loads, this also has a similar drastic drop effect, as we'll see in a minute, over very short time periods in terms of seconds, and under some unusual scenarios, which we'll also show in a second. So we'll get we should be able to get a very similar drastic drop like this, but over very short time periods. So it'll be a similar sort of graph to this one. So just remember that 1.7 ohm value and how it will basically be unmeasurable in the stuff we're going to do today. It won't have an effect at all, yet you will still see the voltage drop on the battery very similar to this sort of thing, because it's not the internal impedance at play. So that is why if we set our multimeter to 10 meg input impedance like that, we're going to get a fairly dramatic drop like that in the initial drop anyway of the voltage of the cell. Now it will actually start out and drop exactly like we saw on the Energizer graph there. Start out very high, drop dramatically, and then sort of taper out and sort of stay steady. So if we leave that there long enough, we will actually see that that value will eventually stabilize. Now with a 9-volt battery and a 10 meg ohm impedance on our multimeter here, we're only talking 900 nanoamps. And of course 900 nanoamps times 1.7 ohms internal resistance, we're only talking about 1.5 microvolts. So really you can't even see 1.5 microvolts on here. It's the next digit over effectively. So, you know, really we're just being swamped by the electrochemical effects here, so we can't actually see our internal resistance of our battery just based on the very light load from this multimeter. But let's have a little play around with this, because we can. Let's go into a high impedance mode, or 10 gig ohms, and let's go into the display and go into the trend chart here. So what I'm going to do is I'm in the 10 gig ohm high Z state, so we're only talking with 10 gig 900 picoamps across a 9-volt battery, so there's effectively no load at all. And if you multiply that by the internal resistance, you know, we're down at 1.5 nanovolts, absolutely tiny. But anyway, let's hook that up, and then we're in our trend chart mode. So let's actually reset our readings on our trend chart here and see what we get. So there we go. I've auto-scaled that, and as you can see, it's sort of, you know, it is pretty flat because it's had time to stabilize from that dramatic 10 meg ohm load, by the way. So what we're going to do now is we're actually going to turn on our 10 meg load. And of course, if you're just talking about the internal resistance of that battery, as I said, here's our voltage here. Now we would expect it if it's just based on the internal resistance, or the nominal internal resistance, so 1.7 ohms, once we put that 10 meg on there, if it's just due to the internal resistance of the battery, then we'd expect the value here, which you can see the numeric result, to only drop by 1.5 microvolts. So we shouldn't expect to see any drop on there at all. But let's do it. Let's switch it on, 10 meg, and bam, look at that. It's dropped right off the scale, so much so that we have to go back in here and auto scale that again, and you can see it drop down fairly dramatically. You know, it's fairly well stabilized there now. You know, there's still a bit more to go, but let's turn it back and we'll watch it jump back up. There it goes. Look at that. And it should curve back up to our original terminal voltage up there. So we've got some funky, very low load, incredibly light load electrochemistry effects happening within the battery there. Now the original commenter said that drop of course had to do with the temperature of my hand in the battery, and that actually has nothing to do with it at all. It's demonstrated that it was actually the load doing that. But let's clear this. Okay, I'm back to 10 meg input impedance here. Now, oh, sorry, I'll get back to displaying recent data. There we go, that's better. There we go. And watch what happens though. This is quite fascinating, okay? Watch what happens if I squeeze this battery. Woohoo! Look at that. Let's auto scale that again. Squeeze again. Look at that. It's jumping all over the shop, just squeezing it. It's electrochemistry effects, once again, causing that to happen. And if we switch back, in this case it's physical. There's some physical process inside that battery. Let's go back, auto scale it again, and here's where we have to let it settle and stuff like that. So this is with a 10 meg load. Let's give that a little squeeze. Look at that. There we go. And it's still doing it. And it's not the leads or anything like that. I mean, you know, I can move this around here, and you know, it's not the contacts. I can sort of, you know, I mean, if I really play around with it, we might be able to get some something to do with the contacts. But that is physically me squeezing that battery. Or if I put it down like that, here we go. Let's auto scale again. There we go. Look at that. Fascinating. And we can put it side on like that. Bingo, it does exactly the same thing. And that is effectively changes in the ionic resistance of that battery due to physical pressure. That was an absolute ripper. Look at that. We got a negative going pulse there. So that is absolutely fascinating, and it takes time to recover because it's the chemical ionic processes within the battery that are actually doing that. And I'm sure you could do a whole PhD thesis on examining exactly what, you know, is going on in various cells of different chemistry in terms of pressure, temperature and discharge current and initial loading discharge and all sorts of, you know, all sorts of stuff. But I find that absolutely fascinating. And I've been playing around with this battery quite a bit, so what I'm going to do is actually just repeat that with a brand new Duracell. So let's whip this one out of the packet and give it a go. Here we go. Let's put it on. Never been loaded. Alright, clear readings and auto scale. There we go, it's dropping down. Oh, we've got the, yeah, we got the 10 meg load on. Oops, let's put the auto on. There we go. So we've got our 10 gig impedance, and that recovered fairly quickly there. But you can see that even with a 10 gig load or greater than 10 gig, the datasheet doesn't actually tell you the exact value of it, but let's assume it's just 10 gig. That's still only 900 picoamps load on that thing, and we can still see the discharge curve of that. Absolutely incredible. There we go. Look at that. That'll take quite some time to stabilize. And let's see if the Duracell has that same effect, where we can apply pressure to it. And, well, yeah, I saw a little blip in there. Yep, there we go. Look at that. But it's a different, looks like it's a different effect to our Vada battery. Check that out. I've actually effectively changed the slope of the discharge of that cell just by, oh, that battery, sorry, it's not a cell, it contains 6 cells, just by squeezing that. Absolutely fascinating. And you can see it's starting to recover there in terms of slope, but let's actually switch on our 10 meg load now and see what we get. There we go. We're dropping about 10 microvolts there per second or thereabouts, but that one didn't show a dramatic effect with the 10 meg load as the Vada battery did with its. I don't know the history of this Vada battery, by the way. It just came out of my drawer. I may have used it once or twice in something. And can we see this same effect with a AA? Well, I've got a Vada long life AA battery here, brand new, straight out of the packet, unused, and let's take a look. I've got it in the high impedance mode at the moment, and there you go. It's fairly flat, it's fairly stabilized, and we can go back and we can auto scale that, of course. Sometimes it doesn't auto scale to the center, but anyway, we should be able to see if there's any pressure effects in this one too. So it's sort of harder to put a bit pressure on a AA, but you can see that yeah, look at that. Let's auto scale that. Check it out. We did get a drop there. Will it recover? I don't know. We'd need some time to actually find that out. And I've left it for just over 20 minutes here, and you can see that it didn't recover at all. There's that little period there where we actually pressed the thing, stepped down, and it looks like I permanently hurt the poor little bugger, and it never recovered at all. Permanently dropped its voltage, and you can see that there is a ramp down. It's a very slow little slope there, drop in voltage over that time. Now, whether or not that's due to the trauma, I guess, of actually pressing that cell, or whether or not it's the very gentle, once again, still high impedance load on this thing or not, I don't exactly know. But anyway, it's interesting. And once again, if you're wondering, no, it doesn't really have anything to do with the context. I've just got my alligator clips hooked on here, and you know, I can play around with this thing and give it a bit of a go there, and really, hey, look at that, maybe a little slight something happening there, but it's not the contacts going dodgy or anything like that, especially at these incredibly low loads. And you can actually see the recovery of the AA Vada cell there when it went down to 10 megohm load, and then I set it back to high impedance mode, and it ramped up over the span of about 30 minutes right back to the original value up there. And you can see with the AA battery here how we dropped down to, I was playing around with it down to 10 megohms load there, then I switched it back to high impedance, and look at the total time, basically 30 minutes there to slowly ramp back up, right up back to the original value there. That shows you how slow changing this ionic electrochemistry is inside these cells. Really quite a slow process. And look at the values we're talking about here. We're barely talking about 100 microvolts there, total change. 4th decimal place stuff. I mean, really small values, but 6.5 digit meter like this, with the actually it's more than 6.5 digits when you're in this trend chart mode, can really show you these differences. One of the benefits of one of these really high resolution digital multimeters. And here's a brand new Duracell AA, fresh out of the pack, long expiry date, and haven't loaded it with 10 megohms. It's on the 10 gigohm thing, so this thing has never been loaded out of the box, and you can see it dropping down, you know, fairly consistently like that until it'll get to a point where it's going to stabilize fairly well. And that is even for that incredibly light 10 gigohm load. Absolutely incredible. And check that out, after 6 minutes, there's our initial drop we saw before, and I thought it was flattening out, but now it's sort of recovering a bit. And there you have it. It's practically recovered to exactly where it was straight factory fresh there. So that initial dip was due to the 10 gigohm load on there, slowly recovered. Well, let's see what happens if we give this thing a little pressure test. No, hardly anything at all on that fresh Duracell. No, no. There we go, got a little something there, but not much at all. And just for kicks, we'll go back to the 9-volt battery, but this time Energizer, fresh out of the pack. Let's give it a go. Here we go, 10 gigohm load, so never been loaded, fresh out of the pack. Clear that, and we will auto scale, and bingo, there we go. We get that initial drop again, every time. And that's over 14 minutes there, and you can see that we haven't had any recovery at all, but we have had a change in slope. I mean, you can see the big large slope there, and then it flattens out a bit, and then we've got sort of another slope down in here. So it's gradually tapering off, but that's after almost 15 minutes. Now, can we actually get a pressure change in that? Well, let's give it a go. No, I'm going to have to switch out of the recent mode. Yeah, there we go. We've got it to change. Auto scale. Yeah, there we go. We changed the slope of it once again, going downwards, just like the Duracell one, and opposite to what we saw in the Vata battery. And there we go. It's starting to level back out. So let's give that a squeeze again. Yep. There we go. Pressure effects once again. And let's see what happens if we switch to 10 megohm mode. There we go. 10 meg, and once again we don't get a huge drop at all. So that brand new Energizer out of the packet effectively shows very little difference at all there between the 10 megohm impedance and the 10 gigohm impedance. That's purely because it's totally fresh. So that Vata battery we were playing with at the start obviously had a little bit of use in it and wasn't, you know, directly factory fresh like this Energizer one or the Duracell. And just for more kicks, we have a Coles brand battery. I have no idea who actually manufactures this one, but we'll give this a go. Check out that one. We got a sudden drastic drop there, and that wasn't me touching this thing at all. Oh, look at that. Look at that. Isn't that unusual? What's going on there? That is really, really weird. Wow. Look at that. Let's turn on. Well, look. See, another drop. I swear I'm not touching that. I am not touching that at all. I won't even breathe on it. Very interesting. Let's see what happens if we switch our 10 megohm load on there. Oh, wow, look at this. This fresh Coles battery, straight out of the packet. We've got ourselves a big drop like we got on the Vata one. So maybe that Vata one wasn't used. Maybe it's just the physical construction is different and the chemistry is, the chemistry is technically the same. But there we go. Yeah, we got the same thing we see in the Vata battery. So there you go. It's not a Vata battery, this one, I know, because this one's made, according to the packet, in South Korea. And, yep, and the Vata one is made in Germany. So there you go. but basically exactly the same thing that we saw in the Vata battery. So that Vata battery, I was fairly sure that hadn't really been used, maybe for 5 minutes in something very light or something at best. But it looks like Cole's one has confirmed that effectively the Duracell and the Energizer ones are almost identical in terms of their response, but this one is very similar to the Vata, almost identical. So let's see if that should recover now if we turn that load back. Yep, yeah, it works exactly the same as the Vata. Look at that. So I reckon that Vata one was actually brand new, and this one has confirmed it. So that was well worth doing, that Coles one. That was very, very interesting. Now let's see what happens if we do the squeeze test. Actually, I won't touch that. We're probably better off clearing that, actually. Starting afresh there. And I'll just turn it off there. So, auto scale. And, let's not wait. Come on, I can't wait. Let's give that a little press. Yep, goes up just like the Vata one. Confirmed. 2 different types. We've discovered 2 different types of alkaline construction 9-volt batteries. Wow, that is fascinating. There's squeeze again. It's done exactly the same thing. Woohoo! This is great. I love playing around with stuff like this. So there you go. I hope you found that interesting and you learned something there. And of course, this isn't, a scientific test. This was just a little quick throw together to show you that, to show the original YouTube commenter that had nothing to do with the temperature of my hand. It was actually the load, even the incredibly light load of the multimeter, combined with the electrochemistry and the ionic resistance in the battery that was causing those drops. But we also played around with the fact that these things are pressure sensitive. If you like that video, please give it a big thumbs up on YouTube, because that always helps a lot. And if you want to discuss it, jump on over to the EEVblog forum. That's the best place to do it, although you can always leave comments in YouTube as well. And if there's enough interest, maybe I might follow this up with some more testing. But if you've got a high resolution multimeter like this, have a play around with this, because this sort of stuff is absolutely fascinating. It would be interesting to see what results we can get if we do some more scientific, more methodical testing on these things. But there you go. Catch you next time.